Okay, so I promised you guys that I would dedicate an entire video to ionic bonds, so that's what I'm going to do. So ionic bonds are always made of two different types of atoms. First of all, they're made with an atom that really wants to give an electron away, and then they're made of an atom that really wants to take an electron. So let me show you what I mean by this. I'm going to color code here. So I'm going to color code atoms that really want to give away electrons. I'm going to color code those in purple. And atoms that really want to take electrons, I'm going to color code that in red. And I'm going to refer to our example we had on the first page of our notes, table salt, sodium chloride. So sodium and chlorine, when they're just atoms, have a certain number of valence electrons. Since sodium is in this first column right here, it has one valence electron. Chlorine, on the other hand, is in our halogens group. And chlorine has 7 valence electrons. Now, last unit we talked about this thing called the octet rule, where atoms would like to have a full octet to be balanced and most stable. So sodium, since it's easier to lose 1 electron than it is to gain 7, sodium is going to want to be an electron giver. And chlorine is going to want to be an electron taker. So chlorine is perfectly matched for sodium in the fact that it wants to take 1 electron and sodium wants to give 1 electron. So they're kind of like a match made in heaven. So when I see this transfer, what I end up getting is sodium with a +1 charge and chlorine with a -1 charge. Now, hopefully you've heard this cheesy phrase, opposites attract. I've mentioned it once or twice. What I mean by that is positive charges are attracted to negative charges and vice versa. So now that these two atoms are ions with opposite charges, there's an attraction between them, kind of like a magnet. Imagine the strongest magnet out there and then multiply its strength by 100. And that's the strength of attraction between these ions. So this attraction makes the ionic bond. So the reason they're connected is the ionic bond. Now, atoms that really want to give away electrons are not just in the first column. In fact, atoms that really like to give away electrons are in the first column and the second column and even this middle block. And even sometimes by the stair step over here. Pretty much any atom that we could call a metal is going to be an electron giver. Now remember, metals are all of the elements that are down and below the stair step. So I'm drawing my stair step right here. I know that I have metalloids along the stair step, but for our purposes, we can just remember that metals are just going to be below the stair step. So for the most part, all of these elements that I have in purple are going to be electron givers. And all of my elements that are above and to the right of the stair step are nonmetals, and they're electron takers. So in order to have an ionic bond, this is the requirement. It must always be between a metal and a nonmetal. We can't have it any other way. An ionic bond isn't going to form between a nonmetal and a nonmetal. It's not going to form between a metal and a metal. It's always got to be between a metal and a nonmetal. And that's going to be very useful for us. So I'm even going to highlight that because it's probably the most important thing that you could take away from this slide. So moving down onto properties. So first of all, if I were to look at the structure of an ionic compound, it's going to look like a crystal. And the reason why it looks like a crystal is because the ions form a crystalline structure. A crystalline structure means that there's a repeating pattern. In this case, my repeating pattern is chlorine, sodium, that alternating pattern, chlorine, sodium, chlorine, sodium, chlorine, sodium. This repeating pattern that we see making up this crystalline structure is called a formula unit. So ionic compounds aren't made of molecules, they're made of formula units. Now, for physical properties, ionic compounds are very difficult to break. It's difficult to break an ionic bond, which means that it's difficult to spread ions out. So if it's difficult to spread ions out, that means it's difficult to melt them and it's difficult to boil them, because melting and boiling requires spreading out the ions. And like I just said, in order to spread them out, we have to break ionic bonds, and that's not an easy thing to do. So if I wanted to spread out ions, I'd have to add tremendous amounts of energy. So what we see with ionic compounds is they have very high melting and boiling points. A high melting and a high boiling point means that I have to add a lot of energy to get to a very high temperature in order to separate those ions, because it just requires that much energy to do so. Now, because we've got this nice crystal structure, it's very, very difficult to move the ions around, so they're not malleable at all. In fact, you could even describe them as being brittle. It's easy to break a crystal. It's not easy to bend a crystal. So a better word to describe an ionic compound would be brittle and not malleable. Now, as far as conductivity goes, ionic compounds are kind of strange. They're very bad conductors as solids. However, they're very good conductors in two instances. They're good conductors as liquids, and they're good conductors when dissolved in water. And we'll talk more about why this is, but for now we just need to remember that ionic compounds are bad conductors as solids, but they're good as liquids, and they're good when dissolved in water. So this concludes my video on ionic compounds. Go ahead and tune into the next video to learn about covalent bonds.